At the heart of the mystery of why some things pass through walls while others cannot lies a simple but powerful idea. Particles and waves interact with matter in very different ways. This difference is not obvious in daily life, because our senses evolved to work in a world where solid objects behave predictably. Walls stop light, floors stop our feet, and doors separate spaces. Yet beneath this familiar experience is a hidden world where matter is mostly empty space, and where interactions, not solidity, decide what can pass and what cannot. To understand this, imagine matter not as a solid block, but as a vast structure made of tiny atoms. Each atom consists of a dense nucleus surrounded by electrons, with enormous distances between them compared to their size. If atoms were scaled up to the size of a stadium, the nucleus would be a marble at the center, and the electrons would be tiny insects buzzing near the outer edges. Everything in between would be empty space. Walls feel solid not because they are packed tightly with material, but because of the forces acting between atoms when they come close together. Now consider waves, especially light. Light behaves as an electromagnetic wave, even though it also has particle-like properties. When light reaches a wall, its electric and magnetic fields interact strongly with the electrons in the atoms of that wall. These electrons are not passive. They respond immediately to the incoming wave, vibrating, absorbing energy, and re-emitting it in different directions. This collective response of trillions of atoms blocks the light, reflects it, or converts it into heat. The wall appears solid and opaque because the interaction between light and matter is strong and unavoidable. Particles, however, come in many forms, and their interactions vary enormously. Some particles behave more like light in how strongly they interact with matter, while others barely notice that matter exists at all. The key point is that passing through is not about size alone, but about interaction strength. A particle can be incredibly small and still be stopped if it interacts strongly, or it can be stopped only rarely if it interacts weakly, even if it passes directly through dense material. This difference becomes clearer when we think about forces. In the universe, particles interact through a small number of fundamental forces. The electromagnetic force is one of the strongest at everyday scales, and it governs how light interacts with matter. Any particle that carries electric charge or interacts electromagnetically is likely to be blocked by ordinary materials. This is why electrons, protons, and most charged particles cannot pass through walls easily. They feel the electromagnetic fields of atoms and are deflected, absorbed, or stopped almost immediately. Waves, too, are subject to these forces. Sound waves require a medium like air or solid material to travel through, and their behavior depends entirely on how the atoms in that medium respond. Light waves, while able to travel through empty space, are deeply affected by the electromagnetic structure of matter. When light encounters a material whose atoms can easily respond to its frequency, it is absorbed or reflected. This is why glass lets visible light through but blocks ultraviolet light, and why metals reflect light so efficiently. Now contrast this with particles that do not interact electromagnetically in the same way. Some particles have no electric charge and interact only through weaker forces. For these particles, the electrons and nuclei inside a wall offer little resistance. They can pass between atoms without triggering any significant response. To such particles, a wall is not a barrier but a sparse forest, with vast empty spaces between the trees. This brings us to an important shift in perspective. In everyday language, we think of walls as objects that block things. In the microscopic world, nothing actively blocks anything. Instead, particles and waves either interact or they do not. If the interaction probability is high, the object appears solid. If the interaction probability is low, the object becomes almost invisible. Light sits on one side of this divide. Its interaction with electrons is so strong that even a thin layer of material can stop it. A single sheet of paper can block light because the photons are absorbed or scattered almost immediately. This makes light an excellent tool for vision, but a poor tool for seeing through solid objects. Other forms of radiation demonstrate how changing the type of wave or particle changes the outcome. X-rays, for example, are also electromagnetic waves, but with much higher energy. They interact differently with matter, passing through soft tissue while being absorbed by denser materials like bone. The wall does not suddenly become less solid. The interaction simply changes. The same structure can be opaque to one form of radiation and transparent to another. At the particle level, this idea becomes even more striking. Neutrinos, for instance, are particles that interact so weakly with matter that trillions pass through your body every second without any effect. They pass through walls, oceans, and even entire planets because the chance of interaction is incredibly small. A neutrino could travel through a wall thicker than the Earth and still have a good chance of emerging on the other side unchanged. This difference between light and such particles is not about intelligence or special ability, but about the fundamental rules governing interactions. Light is built to interact with charged particles. Its very nature is tied to electric and magnetic fields. Particles like neutrinos are governed mainly by forces that rarely come into play at everyday scales. As a result, they slip through matter unnoticed. Quantum mechanics deepens this understanding. At small scales, particles and waves are described by probabilities rather than certainties. When light approaches a wall, the probability of interaction is near 1. Interaction is almost guaranteed. For weakly interacting particles, the probability is close to 0. Most of the time, nothing happens, and the particle continues on its path as if the wall were not there. This probabilistic view changes how we think about barriers. A wall is not an absolute boundary. It is a region where interactions are likely. The stronger the interaction, the more solid the barrier appears. The weaker the interaction, the more transparent the barrier becomes. This principle is not limited to exotic particles. It appears in everyday technology. Radio waves pass through walls more easily than visible light because they interact differently with matter. This is why Wi-Fi signals can reach different rooms even when light cannot. The wall remains the same, but the interaction changes. Understanding that particles and waves interact with matter in fundamentally different ways helps explain not only why some things pass through walls, but also why the universe is structured the way it is. Stars shine because light interacts strongly with matter. The sun's energy reaches Earth because space is mostly empty, offering little resistance. At the same time, deep inside the sun, particles escape that light cannot, carrying information from regions we could never see with our eyes. This hidden framework reshapes our idea of solidity. What we experience as solid is the result of countless interactions happening at once, governed by electromagnetic forces and quantum rules. Remove or weaken those interactions, and solidity disappears. Walls stop light not because they are truly solid in an absolute sense, but because light is exquisitely sensitive to the structure of matter. In the end, the difference between particles and waves is not just a technical detail of physics. It is a reminder that reality depends on perspective. From a human viewpoint, walls divide space. From the viewpoint of certain particles, those same walls barely exist. The universe allows both views at once, unified by the simple but profound idea that interaction, not material thickness, determines what can pass and what cannot. This understanding forms the foundation for exploring deeper questions about the universe. Once we accept that matter is mostly empty space and that interaction strength defines reality, the idea of particles passing through walls no longer seems magical. It becomes a natural consequence of how different forms of energy and matter engage with the fabric of the physical world. Light feels effortless and intangible. It fills rooms instantly, reveals colors, and allows vision without any sense of weight or resistance. Because of this, it is natural to assume that light should pass through most things easily. Yet a thin curtain can dim it, a wall can stop it completely, and even a sheet of paper can block it almost entirely. The reason for this is not that light is weak, but that it interacts extremely strongly with atoms. That interaction, invisible to us, is what makes walls opaque and gives matter its familiar appearance. To understand why light is so easily blocked, it helps to rethink what light actually is. Light is a form of electromagnetic radiation. It carries energy in oscillating electric and magnetic fields that move through space at an incredible speed. These fields are not abstract ideas. They are real physical influences. Any particle with electric charge responds to them, and atoms are full of charged particles. Every atom contains negatively charged electrons bound to a positively charged nucleus. These electrons are constantly sensitive to electric fields, even very weak ones. When light reaches a material, it does not simply collide with it like a ball hitting a wall. Instead, its oscillating electric field immediately begins to influence the electrons in the atoms it encounters. The electrons are forced to move, vibrate, or shift their positions in response to the changing field. This happens on timescales far too short for us to perceive, but it is the fundamental reason light cannot pass through most solid objects. The strength of this interaction is crucial. The electromagnetic force is one of the most powerful forces in nature at the scale of atoms. It is vastly stronger than gravity and dominates nearly all everyday physical interactions. Because light is itself an electromagnetic phenomenon, it couples directly to this force. When light encounters matter, it is interacting with one of the strongest available mechanisms in the universe. As electrons respond to incoming light, several outcomes are possible. In some cases, the electrons absorb the energy of the light, using it to jump to higher energy states within the atom. This absorbed energy may later be released as heat or re-emitted as light of a different wavelength. In other cases, the electrons re-emit the light almost immediately, sending it back in another direction. This is what reflection is. When trillions of atoms do this collectively, the material appears opaque or reflective rather than transparent. The key point is that these interactions happen extremely efficiently. Light does not need to penetrate deeply into a material to be stopped. Even a very thin layer of atoms provides enough charged particles to interact with nearly all incoming photons. This is why walls do not need to be thick to block light. A surface layer only a fraction of a millimeter deep is often enough to absorb or scatter most of it. Transparency, when it occurs, is not the absence of interaction, but a very specific kind of interaction. Materials like glass are transparent to visible light because their electrons cannot easily absorb photons of visible wavelengths. Instead, the electrons respond by briefly vibrating and then re-emitting the light in the same direction. To us, it appears as though the light has passed straight through. In reality, it has been absorbed and re-emitted countless times at the atomic level, delayed slightly and redirected in a way that preserves the image. This delicate balance explains why transparency is selective. Glass that is transparent to visible light may block ultraviolet light or infrared radiation. Change the frequency of the light, and the interaction changes. The same atoms that ignore visible light may strongly absorb higher energy ultraviolet photons. This is why sunlight can pass through windows, while harmful ultraviolet radiation is partially blocked. Walls made of wood, concrete, or metal behave differently because their atomic structures allow electrons to absorb or scatter visible light efficiently. In metals, free electrons move easily in response to light's electric field, re-emitting it almost instantly. This is why metals are shiny and reflective. In materials like concrete or brick, the irregular arrangement of atoms scatters light in many directions, preventing it from passing through and giving the surface a dull appearance. What makes this especially striking is that light is stopped not by solidity in the everyday sense, but by electromagnetic responsiveness. The wall does not act as a rigid barrier that physically blocks photons. Instead, it acts as a responsive medium that reacts so strongly to light that the light cannot continue its original path. The photons are absorbed, redirected, or transformed almost immediately upon contact. This also explains why increasing the energy of light changes how deeply it can penetrate matter. X-rays, which are much higher in energy than visible light, interact differently with electrons. They can pass through soft tissues because the electrons there do not absorb them as efficiently. However, denser materials with tightly bound electrons, such as bone or metal, absorb X-rays more strongly. The interaction is still electromagnetic, but the details depend on energy and atomic structure. Even gamma rays, the most energetic form of light, are not immune to interaction. Given enough material, even gamma rays can be absorbed or scattered. There is no form of light that can pass through matter indefinitely without interacting. The difference lies only in how far it travels before that interaction occurs. From this perspective, the opacity of walls is not a special feature, but a natural consequence of how light works. Light is designed, by its very nature, to interact with charged particles. It is the messenger of electromagnetic force, and atoms are built from charged components. The meeting of the two is inevitable and intense. This strong interaction is also what makes light so useful. Vision depends on light interacting with the atoms in our eyes. Colors arise because different materials absorb and reflect different wavelengths. Heat from sunlight warms the earth because light transfers energy to atoms in the atmosphere and on the surface. Without this strong interaction, light would pass through everything unnoticed, and the visible world as we know it would not exist. The same principle explains why darkness occurs behind walls. Light does not bend easily around obstacles at everyday scales because its wavelength is much smaller than most objects. When it hits a wall, it does not diffract significantly. Instead, it interacts directly with atoms and is stopped. The shadow is not the absence of light everywhere, but the result of light being prevented from reaching certain regions due to strong atomic interactions. It is also important to recognize that light is not unique in this respect among waves. Any wave interacts with a medium based on how strongly the medium can respond to it. Sound waves, for example, are vibrations of matter itself. A wall blocks sound because it prevents air vibrations from passing easily through, though some energy can still be transmitted. Light, however, does not need a medium to travel, yet it is still deeply affected by matter once it encounters it. This leads to a subtle but powerful insight. The fact that light is blocked by walls does not mean walls are impenetrable in an absolute sense. It means that walls are made of atoms whose electrons are highly responsive to electromagnetic disturbances. Light happens to be exactly such a disturbance. Change the type of disturbance, and the wall's effectiveness changes. This is why radio waves can pass through walls more easily than visible light. Their longer wavelengths interact differently with electrons, often passing through materials that appear opaque to our eyes. The wall has not changed, only the nature of the electromagnetic wave has. Seen this way, the blocking of light is not a limitation of light, but a consequence of its intimate connection to matter. Light is the language atoms speak fluently. When it arrives, they answer immediately. That conversation, happening trillions of times per second at the atomic level, is what creates shadows, reflections, colors, and the apparent solidity of the world. In the end, light is easily blocked because it is never ignored. Atoms cannot help but respond to it. Their charged particles vibrate, absorb, and re-emit its energy with extraordinary efficiency. What we perceive as a solid wall is, at the deepest level, a dense field of electromagnetic interactions that leave light with no clear path forward. This relentless responsiveness is why light reveals the world to us, and also why it cannot slip quietly through the walls that surround us. There are particles in the universe that behave in a way that seems almost supernatural when compared to everyday experience. They move through walls, pass through mountains, and even travel through the entire Earth without slowing down or changing direction. This does not happen because they are fast, clever, or made of some special ghostly substance. It happens because they interact with matter so weakly that, for most practical purposes, matter does not exist to them at all. This idea, that some particles have extremely weak interactions with matter, is one of the most important concepts for understanding why the universe behaves the way it does beneath the surface of what we can see. To grasp this idea, it helps to first think about what interaction really means. In daily life, interaction feels obvious. When you touch a wall, your hand stops. When light hits the wall, it reflects or is absorbed. These events feel automatic, but at the microscopic level, they depend entirely on forces acting between particles. Nothing ever truly touches anything else. What happens instead is that particles influence one another through forces. If the force is strong, the interaction is obvious. If the force is weak, the interaction may never be noticed. Matter, as we experience it, is held together and made solid by strong electromagnetic interactions. The electrons in atoms repel the electrons in other atoms, creating resistance and structure. This is why you cannot pass your hand through a wall. Your atoms are being powerfully repelled by the atoms in the wall long before they ever overlap. The sense of solidity is the result of these interactions, not of atoms being packed tightly together. Now consider a particle that does not participate in these interactions in the same way. If a particle has no electric charge, it does not respond to electromagnetic forces. If it also does not interact strongly through other forces, then the atoms in a wall have no effective way to stop it. The particle does not feel the electromagnetic push that normally defines solidity. To such a particle, the wall is not a solid barrier, but an almost completely empty region of space. This is not a theoretical idea alone. It happens constantly around you. One of the most famous examples is the neutrino. Neutrinos are produced in enormous numbers by the sun, nuclear reactions, exploding stars, and even the natural radioactive processes inside the Earth. Every second, billions of neutrinos pass through your body. You do not feel them. They do not heat you, push you, or leave any noticeable trace. They are there, but they might as well not be, because their interactions with your atoms are incredibly rare. The weakness of these interactions comes from the fundamental forces involved. The universe operates through a small set of forces, and not all particles respond to all of them. The electromagnetic force dominates everyday life because it is strong and has long range. Gravity is also long range, but much weaker at small scales. The strong force binds atomic nuclei together, but acts only at extremely short distances. The weak force, despite its name, plays a role in certain types of particle decay and nuclear reactions, but it is very limited in range and strength. Particles like neutrinos interact primarily through the weak force and gravity. Gravity is far too weak to matter at the scale of individual particles, and the weak force acts only under very specific conditions. As a result, the chance that a neutrino will collide with an atom as it passes through a wall is extraordinarily small. Most neutrinos travel through light, years of solid matter without interacting at all. This idea challenges the way we instinctively think about barriers. In the human world, barriers are absolute. A wall stops you every time. A door blocks sound unless it is open. At the particle level, barriers are statistical. A wall does not guarantee an interaction. It only increases the chance of one. For strongly interacting particles, that chance is so high it feels like certainty. For weakly interacting particles, the chance is so low it feels like impossibility. Imagine firing billions of tiny arrows through a vast forest where the trees are spaced miles apart. Most arrows would pass through without ever hitting a tree. Now imagine a dense forest where the trees are packed tightly together. Almost every arrow would hit something. The forest has not changed its basic nature. Only the spacing and likelihood of collision have changed. Matter is like that forest, and particles differ in how likely they are to strike a tree. For weakly interacting particles, atoms are spaced far apart relative to the particle's probability of interaction. The particle passes between nuclei and electrons without being deflected. Even though matter is everywhere, interaction almost never happens. This is why these particles can pass through walls, planets, and stars as if they were not there. What makes this even more remarkable is that these particles are not especially small in a classical sense. Size is not the key factor. Interaction strength is. A particle can be point-like and still interact strongly, or it can be point-like and interact barely at all. The difference lies in how it couples to forces, not in its physical dimensions. This weakness of interaction has profound consequences for science. Because neutrinos and similar particles pass through matter so easily, they can escape from environments that trap light. The core of the sun, for example, is so dense that light takes thousands of years to slowly make its way to the surface. Neutrinos produced in the same region escape almost instantly and reach Earth in minutes. By detecting them, scientists gain direct information about processes happening deep inside the sun that would otherwise be hidden. The same is true for distant cosmic events. When a massive star collapses or explodes, light may be delayed, absorbed, or scattered by surrounding material. Weakly interacting particles escape immediately, carrying information about the event's earliest moments. In this way, particles that ignore walls become messengers from regions of the universe that light cannot easily reach. The difficulty, of course, is detection. Because these particles interact so weakly, detecting them requires enormous instruments and extreme patience. Scientists build massive underground detectors filled with water, ice, or other materials, hoping that once in a very long while, a passing particle will interact with an atom and produce a tiny flash of light or a faint signal. Most particles pass through unnoticed, but the few that do interact provide invaluable information. This extreme weakness also means these particles are not dangerous in everyday situations. The fact that billions pass through you every second has no effect on your health. They do not damage cells or deposit energy in a meaningful way. Their presence is a reminder that the universe is far more active than we can sense, filled with invisible travelers moving through us constantly. At a deeper level, the existence of weakly interacting particles forces us to rethink what it means for something to exist. These particles are real. They have mass, energy, and momentum. They influence the universe on large scales. Yet they are almost completely disconnected from ordinary matter. Their reality does not depend on interaction with us, and our inability to perceive them directly does not diminish their importance. This concept also connects to one of the biggest mysteries in modern science. A large portion of the universe appears to be made of something that interacts very weakly with normal matter. This unseen component shapes galaxies and influences cosmic structure, yet it neither emits nor absorbs light. The idea that particles can exist while barely interacting with matter is central to understanding this hidden side of the universe. From a philosophical perspective, weak interaction reveals that the world we experience is only a narrow slice of reality. Our senses evolved to detect strong interactions, light, sound, pressure, heat. They tell us nothing about particles that pass through walls without resistance. Technology extends our reach, but even then, detection depends on interaction. If something interacts too weakly, it remains invisible unless we build extraordinary tools to find it. This does not mean that walls are illusions. They are real and effective within the domain of strong interactions. For humans, walls work perfectly. For certain particles, walls are irrelevant. Both views are true at the same time. Reality does not choose one scale over another. It accommodates all of them. The idea that interaction strength defines experience also explains why the universe can be layered with different kinds of phenomena occupying the same space. Atoms, light, weakly interacting particles, and gravitational effects all coexist, passing through one another according to their own rules. Space is not empty, it is shared. In this sense, weakly interacting particles reveal a hidden freedom in nature. They move through structures that confine everything else. They are not bound by surfaces, containers, or barriers. Their paths are shaped by vast cosmic processes rather than local obstacles. This freedom is not magical. It is a direct consequence of the forces they do or do not respond to. When we say that some particles can pass through walls, we are really saying that walls are not universal obstacles. They are effective only against things that interact strongly enough to notice them. For particles that do not, walls lose their meaning. The universe does not grant special privileges. It simply follows consistent rules. Understanding this changes how we think about solidity, separation, and boundaries. It shows that the apparent firmness of the world is not an absolute property, but an emergent one, arising from strong interactions among particles like us. Beyond that familiar layer lies a quieter, subtler reality where matter becomes transparent and movement is almost unrestricted. In the end, the extreme weakness of interaction is not a flaw or limitation. It is a feature that allows the universe to communicate across otherwise inaccessible regions, to preserve information from deep interiors, and to host forms of existence that do not conform to human intuition. Particles that pass through walls remind us that the universe is not built around what we can feel, but around deeper principles that operate whether we notice them or not. When people hear that particles can pass through solid objects, the idea often sounds like science fiction. Solid objects feel absolute. They define boundaries, protect spaces, and separate one place from another. In everyday life, nothing larger than a molecule ever slips through a wall. Yet at the microscopic level, nature follows rules that are very different from human intuition. Quantum mechanics provides the framework that explains how particles can cross barriers that seem impossible from a classical point of view. This explanation does not rely on magic or exceptions, but on a radically different way of understanding motion, position, and possibility itself. Classical physics, the kind that governs falling objects and moving cars, treats particles like tiny solid balls. In this view, an object either has enough energy to overcome a barrier or it does not. If a ball rolls toward a hill and lacks the energy to climb it, it rolls back. There is no ambiguity. The barrier is absolute. This logic works extremely well for large objects and is deeply embedded in human thinking. Walls stop things because they are barriers, and that feels final. Quantum mechanics breaks this certainty. At very small scales, particles do not behave like tiny balls following precise paths. Instead, they are described by wave, like mathematical objects that represent probabilities rather than definite trajectories. A particle does not have a single exact position until it is measured. Instead, it exists as a spread out pattern of possibilities. This shift in perspective is the key to understanding how barriers lose their absolute nature. In quantum mechanics, a particle approaching a wall is not just a point moving toward an obstacle. It is a wave, like presence spread across space. When this wave reaches a barrier, part of it interacts with the barrier, but part of it can extend into and even beyond the barrier. If the conditions are right, there is a small but real chance that the particle will appear on the other side, even if it does not have enough energy to cross the barrier in the classical sense. This phenomenon is known as quantum tunneling. The word tunneling is a metaphor, not a literal description. The particle does not dig a hole through the wall or break it apart. Instead, the rules governing probability allow the particle's presence to exist on both sides of the barrier at once. When a measurement occurs, the particle may be found on the far side. The wall has not been violated. The classical idea of an impenetrable barrier simply does not apply at that scale. This behavior arises because energy and position are not as rigidly defined as classical physics assumes. In the quantum world, there is an inherent uncertainty built into nature. A particle's energy can fluctuate slightly for very short periods of time, and its position cannot be pinned down precisely. These uncertainties are not due to measurement errors or lack of knowledge. They are fundamental features of reality. Because of this uncertainty, barriers become regions of reduced probability rather than absolute limits. Inside a solid object, the probability of finding a particle may be extremely low, but it is not necessarily zero. For very small particles and very thin barriers, that probability can become significant enough to matter. Over time, even a tiny chance can produce real, observable effects. This is not just a theoretical idea. Quantum tunneling is essential to many natural processes. Nuclear reactions inside stars depend on tunneling. The positively charged nuclei in a star's core repel each other strongly. Classically, they should never get close enough to fuse. Quantum mechanics allows them to tunnel through the energy barrier created by their mutual repulsion, enabling fusion to occur. Without this effect, stars would not shine, and life as we know it would not exist. Tunneling also plays a role in radioactive decay. Certain atomic nuclei are stable only because particles inside them are confined by energy barriers. Over time, one of these particles may tunnel out of the nucleus, leading to decay. This process is inherently probabilistic. There is no exact moment when decay must occur, only a likelihood over time. Again, a barrier that seems solid and permanent is revealed to be permeable under quantum rules. When it comes to particles passing through solid objects like walls, quantum mechanics provides a similar explanation, though the probabilities involved are usually extremely small. A wall is made of atoms arranged in a lattice, with electromagnetic forces holding them together. For large particles or objects made of many atoms, the probability of all their components tunneling through the wall at once is so unimaginably small that it never happens in practice. This is why people do not walk through walls. For individual particles, however, the story is different. An electron, for example, can tunnel through thin layers of material. This effect is used in modern technology, such as scanning tunneling microscopes, which allow scientists to image individual atoms. The microscope works precisely because electrons can pass through barriers that would be impassable under classical rules. The reason tunneling becomes negligible for larger objects is not because the rules change, but because probabilities compound. A single particle has a small chance of tunneling. An object made of trillions of particles would require all of them to tunnel in a coordinated way. The combined probability becomes so close to zero that it effectively never occurs within the lifetime of the universe. Quantum mechanics allows it in principle, but reality never provides the opportunity. This highlights an important idea. Quantum mechanics does not contradict everyday experience. It explains why everyday experience is so consistent. The same rules that allow particles to pass through walls also explain why walls work perfectly well at human scales. The difference lies in scale and probability, not in separate sets of laws. Another key aspect of quantum mechanics is that particles do not move through matter in straight, uninterrupted paths. Their motion is influenced by wave interference, probability distributions, and interactions with fields. When a particle encounters a solid object, it does not see a smooth surface. It encounters a complex landscape of forces, energy levels, and potential barriers at the atomic scale. In some cases, this landscape allows pathways through regions that appear forbidden in classical terms. This idea reshapes the concept of solidity itself. A solid object is not a continuous, impenetrable block. It is a structured arrangement of atoms with spaces between them and forces acting among them. Quantum mechanics describes how particles interact with this structure, not as collisions between hard surfaces, but as interactions between wave, functions, and energy fields. The ability of particles to pass through solids also depends on their quantum properties, such as wavelength. Smaller particles often have longer wavelengths, making tunneling more likely. Heavier particles tend to have shorter wavelengths, reducing the effect. This relationship explains why electrons can tunnel relatively easily, while larger particles rarely do. Quantum mechanics also introduces the idea that observation plays a role in outcomes. Until a particle is detected, it exists in a superposition of possibilities. It is not accurate to say it is definitively on one side of the wall or the other. Only when an interaction strong enough to count as a measurement occurs does the particle appear in a specific location. This does not mean consciousness controls reality, but it does mean that interaction defines outcomes. In the context of walls, this means that a particle passing through is not a tiny object sneaking through a crack. It is a manifestation of probability resolving itself in a way that classical intuition finds surprising. The wall does not fail. The particle simply follows rules that do not align with everyday expectations. Over time, quantum mechanics has shown that nature is less rigid and more flexible than once believed. Boundaries exist, but they are statistical rather than absolute. Possibilities exist even where intuition says there should be none. This does not make the world unpredictable in a chaotic sense. On the contrary, quantum rules are precise and consistent. They are simply different from the rules that govern large-scale objects. Understanding this helps explain why particles can pass through solid objects while light or people cannot. Light interacts strongly with matter and is governed by different constraints. Large objects involve too many particles for tunneling to matter. Individual particles live in a regime where probability and uncertainty dominate, allowing behaviors that seem impossible at larger scales. This perspective also changes how we think about the universe. Space is not neatly divided into accessible and inaccessible regions. Instead, it is a continuous field of possibilities shaped by forces and probabilities. Barriers reduce likelihoods. They do not impose absolute bans. At the smallest scales, the universe is less about what must happen and more about what can happen. Quantum mechanics does not remove mystery from the world. It reframes it. The mystery is no longer how particles cheat the rules, but how the rules themselves differ so profoundly from everyday assumptions. Particles do not break through walls. They exist in a reality where walls are not absolute in the first place. In the end, the ability of particles to pass through solid objects is not an exception to physical law. It is one of the clearest demonstrations of those laws at work. Quantum mechanics reveals a universe where solidity is emergent, boundaries are probabilistic, and the impossible becomes merely unlikely. What feels solid and final to human experience is, at a deeper level, negotiable, governed by rules that allow matter and energy to behave in ways that challenge intuition but remain perfectly consistent within the fabric of reality. Some of the most important discoveries about the universe have come not from what we can see, but from what can pass through everything in its way. There are particles so elusive that they ignore walls, planets, and even stars, yet their behavior has transformed our understanding of reality. These particles, especially neutrinos, have become powerful tools for scientists, allowing them to study regions of the universe that light can never reach. Their ability to pass through matter is not just a strange property. It is a gateway to knowledge that would otherwise remain forever hidden. To understand why this matters, it is important to consider the limitations of light. Light is our primary source of information about the universe. Telescopes collect it, eyes perceive it, and instruments analyze it. Almost everything we know about distant objects comes from the light they emit or reflect. But light has a weakness. It interacts strongly with matter. Dense regions block it, scatter it, or absorb it completely. Wherever matter is thick or turbulent, light struggles to escape. The universe is full of such hidden places. The core of the Sun is one example. It is a region of immense density and pressure where nuclear reactions power the star. Light created in the core does not travel straight out into space. Instead, it is absorbed and re-emitted countless times, slowly diffusing outward over thousands or even millions of years. By the time sunlight reaches Earth, it carries little direct information about the precise conditions at the sun's center. Neutrinos change this situation entirely. These particles are produced in huge numbers during nuclear reactions, including those in the sun's core. Unlike light, neutrinos interact extremely weakly with matter. The dense plasma of the sun barely affects them. They escape almost instantly, traveling straight from the core to space and reaching Earth in just over 8 minutes. By detecting them, scientists gain direct evidence of the processes happening deep inside the sun right now, not thousands of years ago. This ability turns neutrinos into messengers from inaccessible regions. They carry information from places that light cannot leave in a meaningful way. When scientists measure neutrinos arriving on Earth, they are effectively looking directly into the heart of a star. This has allowed researchers to confirm theories about how the sun produces energy and to test models of nuclear fusion under extreme conditions. The same principle applies on a much larger and more dramatic scale. When massive stars collapse and explode as supernova, the core becomes so dense that light is trapped. The explosion may take hours or days to become visible, and even then, much of the internal process remains hidden behind layers of debris. Neutrinos, however, are released in enormous bursts during the collapse. They escape immediately, carrying information about the earliest moments of the explosion. In one historic case, neutrinos from a supernova in a nearby galaxy were detected on Earth before the explosion became visible through telescopes. This marked a turning point in astronomy. It showed that scientists could observe cosmic events not just through light, but through particles that pass through matter almost unaffected. A new way of observing the universe was born. This approach is sometimes called particle astronomy, and it exists because of the unique properties of weakly interacting particles. These particles do not replace light as a source of information, they complement it. Light tells us about surfaces, temperatures, and compositions. Weakly interacting particles tell us about interiors, cores, and processes hidden behind thick layers of matter. The importance of this extends beyond stars and explosions. Deep inside Earth, radioactive processes generate heat and drive geological activity. Light cannot escape from these regions, and direct observation is impossible. Yet particles produced by these processes travel upward through rock and emerge at the surface. By detecting them, scientists learn about the composition and behavior of Earth's interior without drilling thousands of kilometers into the planet. This same principle is used in studying the universe on the largest scales. Some of the most violent and energetic events occur near black holes and other extreme environments. In many cases, light emitted near these regions is absorbed by surrounding matter or distorted beyond recognition. Weakly interacting particles escape without being deflected, preserving information about where they came from and how they were produced. The challenge, of course, is detection. Because these particles interact so weakly, they are extremely difficult to observe. Scientists must build enormous detectors, often deep underground or under ice, to shield them from other sources of interference. These detectors wait patiently for the rare moments when a particle does interact, producing a tiny flash or signal. Each detection is precious because it represents information that cannot be obtained in any other way. The effort is worthwhile because these particles provide a kind of honesty that light sometimes lacks. Light can be scattered, absorbed, or reprocessed many times before reaching us, blurring its origin. Weakly interacting particles travel in straight lines from their source, largely unchanged. When one is detected, it points directly back to where it was created. This makes it possible to trace events across vast distances with remarkable accuracy. This ability has also helped scientists test fundamental theories of physics. By studying how these particles behave, how many arrive, and how their properties change during travel, researchers have uncovered surprises that forced revisions to existing models. In some cases, particles once thought to be massless were found to have tiny masses. Such discoveries have profound implications for understanding the structure of matter and the evolution of the universe. Beyond specific discoveries, the broader significance lies in how this changes our view of knowledge itself. For most of human history, what could not be seen or touched was considered unknowable. The idea that something could pass through walls without effect seemed irrelevant or imaginary. Modern physics has shown that invisibility does not mean insignificance. Some of the most important carriers of information are precisely those that interact the least. This has philosophical implications as well. It reminds us that reality is not limited to what our senses evolved to perceive. The universe operates on many levels at once, with different forms of matter and energy coexisting in the same space. Walls, planets, and stars define boundaries for us, but they are not universal boundaries. Other entities move freely through them, shaping events in ways we are only beginning to understand. The ability of particles to pass through matter also encourages humility in scientific observation. It highlights that every method of observation has limits. Light-based astronomy once seemed complete, yet it revealed only part of the picture. By embracing new messengers, scientists expanded their reach. Each new window into the universe reveals not just answers, but new questions. In practical terms, this research has also driven technological innovation. The need to detect rare interactions has led to advances in materials, sensors, and data analysis. These technologies often find applications beyond fundamental science, influencing fields such as medical imaging, radiation detection, and data processing. Knowledge gained from studying particles that pass through walls does not remain confined to theory. It ripples outward into everyday life. There is also a poetic aspect to this idea. The universe is constantly communicating, sending messages through space and matter. Some messages are loud and obvious, like visible light from stars. Others are quiet and subtle, passing unnoticed through everything in their path. Learning to listen to these quieter signals has revealed a deeper and more complete story of the cosmos. In this sense, weakly interacting particles act as witnesses. They observe events from the inside and carry that testimony outward without distortion. They are present where light is trapped, where matter is dense, and where conditions are extreme. Their journeys connect distant regions of space and time, linking the birth of stars, the death of galaxies, and the inner workings of planets. Understanding and using this hidden ability has reshaped modern science. It has shown that walls are not absolute, that observation does not require direct access, and that the universe offers multiple channels through which it can be understood. Each channel reveals a different layer of truth. As research continues, these particles may uncover even deeper mysteries. They may help explain the nature of unseen matter that holds galaxies together or reveal processes that occurred in the earliest moments after the universe began. Their weak interaction, once seen as an obstacle, has become their greatest strength. Ultimately, the significance of particles that pass through walls lies not just in their strange behavior, but in what they allow us to know. They remind us that the universe is more transparent than it appears, provided we learn how to look. By following particles that ignore barriers, science has learned to move beyond its own limits, seeing into places once thought forever hidden and discovering that the walls separating knowledge from mystery are far thinner than they seem. Understanding why some particles can pass through walls while light cannot ultimately changes how we see the universe itself. It reveals that reality is not built from solid, impenetrable objects, but from interactions, probabilities, and relationships that operate far below the level of human perception. What appears firm and absolute in everyday life is, at a deeper level, flexible and conditional. This realization has reshaped science and forced humanity to rethink what it means to understand the world. For centuries, people assumed that the universe was made of solid matter moving through empty space. Objects were thought to have clear boundaries, and those boundaries defined what was possible. A wall was a wall because it stopped things. Light was light because it revealed surfaces. These assumptions worked well for ordinary experience and early science. But as researchers began probing smaller scales, those assumptions started to fail. The discovery that matter is mostly empty space was the first major crack in this picture. Atoms, once thought to be tiny solid units, turned out to be vast regions of emptiness dominated by forces rather than substance. This alone suggested that solidity was not a fundamental property, but an emergent one. The fact that particles could move through matter without resistance made this conclusion unavoidable. As scientists explored deeper, they found that the behavior of particles depends not on what matter is made of, but on how particles interact with it. Light cannot pass through walls because it interacts strongly with electrons. Certain particles pass through because they barely interact at all. The wall itself has not changed. What changes is the relationship between the wall and whatever encounters it. Reality, it turns out, is relational. This insight has profound consequences. It means that what we experience is not the full story, but a filtered version shaped by the limits of our senses and the forces we respond to. Humans are sensitive to electromagnetic interactions. Our eyes detect light, our skin feels pressure, and our ears hear vibrations in air. Everything we call real is tied to these interactions. Particles that do not interact in these ways pass through our lives unnoticed, even though they are present in enormous numbers. This challenges the idea that perception defines reality. The universe does not privilege what we can see or touch. It contains layers of activity that overlap in the same space, but remain hidden because they interact too weakly to register. Walls, floors, and bodies coexist with streams of particles that ignore them completely. Space is not divided into occupied and unoccupied regions. It is shared. Recognizing this has transformed how scientists study nature. Instead of assuming that observation must involve direct contact or visibility, researchers now design experiments that rely on rare interactions, indirect signals, and statistical patterns. Knowledge no longer requires control or confinement. It can come from patiently observing what usually goes unnoticed. This shift has also influenced how scientists think about limits. In classical thinking, limits were absolute. You could not see inside a star, look through the earth, or observe the earliest moments of the universe. The discovery of particles that pass through matter showed that these limits were not imposed by nature itself, but by the tools and assumptions we used. By changing the tools, the limits moved. The universe, once thought to be opaque and compartmentalized, began to appear more transparent. Information, flows through matter in unexpected ways. Signals escape from places that light cannot leave. Events announce themselves long before they become visible. Reality turns out to be far more communicative than it seems. This understanding also unifies very different areas of science. The same principles that explain why particles pass through walls also explain how stars shine, why radioactive decay occurs, and how modern technologies function. It shows that nature operates according to a small set of deep rules, applied consistently across all scales. There is no separate logic for the microscopic and the cosmic, only differences in scale and probability. At a deeper level, this realization alters the meaning of explanation itself. Explaining a phenomenon is no longer about describing what blocks what, but about identifying which interactions matter and which do not. A wall is not defined by its hardness, but by the forces it can exert. Transparency is not a property of objects alone, but of relationships between objects and waves or particles. This relational view also helps resolve apparent contradictions. It explains how something can be solid and permeable at the same time. Solid for humans, permeable for neutrinos. Both descriptions are correct within their respective contexts. Reality does not choose one truth over the other. It accommodates both without conflict. There is also a humbling aspect to this insight. It reminds us that human experience occupies a narrow band of possibilities. The universe is not designed to be intuitive. What feels impossible may simply be improbable, and what feels solid may simply be strongly interactive. Our intuition is a product of evolution, not a guide to fundamental truth. This has philosophical implications that extend beyond physics. It suggests that boundaries, whether physical or conceptual, may be less absolute than they appear. Just as walls do not stop all particles, limits in knowledge may not be as final as once believed. History shows that many barriers fell not because reality changed, but because understanding deepened. The idea also encourages intellectual humility. Each generation of science uncovers layers that previous generations could not imagine. The discovery of weakly interacting particles did not invalidate earlier knowledge. It expanded it. In the same way, future discoveries may reveal new forms of interaction that further reshape our picture of reality. In practical terms, this deeper understanding continues to influence technology and research. Detectors designed to observe rare particle interactions push the limits of precision and scale. Data analysis techniques developed for these experiments find applications in medicine, engineering, and computing. The pursuit of invisible phenomena produces visible benefits, yet perhaps the most important impact is conceptual. Learning that particles can pass through walls while light cannot teaches that the universe is not built from rigid objects, but from dynamic processes. What exists is not just matter, but interaction. What matters is not thickness or strength, but how entities respond to one another. This perspective also restores a sense of wonder. The ordinary world, once taken for granted, becomes extraordinary when seen through this lens. A wall is no longer just a barrier, it is a selective filter. A room is no longer empty, it is full of unseen motion. Space itself becomes active rather than passive. The universe revealed by this understanding is richer, subtler, and more interconnected than common sense suggests. It is a place where multiple realities overlap without interfering, where information travels through unexpected channels, and where absence is often just invisibility. In the end, the hidden ability of particles to pass through walls is not a strange exception, but a clue to the true nature of reality. It shows that the world is governed by principles that favor consistency over intuition and depth over appearance. Light stops at walls because it must. Some particles pass through because they can. Both outcomes arise from the same underlying laws. By uncovering these laws, science has not diminished the world, but expanded it. What once seemed solid and final now appears open and layered. The universe, rather than being a closed box of rigid structures, reveals itself as a complex network of interactions where even the strongest barriers are, in the right context, negotiable. This understanding leaves us with a powerful lesson. Reality is not defined by what we can easily observe, but by what exists and interacts, whether we notice it or not. Walls may define our spaces, but they do not define the universe. The deeper we look, the more we find that nature is not confined by the boundaries we take for granted, and that knowledge itself can pass through walls once thought impenetrable.